Welcome to Understanding Behavior Through First-Person Vision. Our presenter today is Dr. James M. Rehg. Dr. Rehg is a professor in the School of Interactive Computing at Georgia Tech. He is also the co-director of the Georgia Tech Computational Perception Lab and director of the Center for Behavioral Imaging. Dr. Rehg also serves as deputy director of the MD2K Center.
So let's get started. So in this talk, I'm going to describe some work we're doing in using a sensing approach from computer vision known as first-person vision to understand behavior in a number of different contexts. And this is work that's been done here with my colleague Agata Rozga and three Ph.D. students, Alireza, Fathi, and Yin Li. So here's, of course, the situation that we're in right now. We have this unprecedented opportunity to capture the visual world as people experience it. So these are several examples of wearable camera systems that are in the marketplace, that are being used by a variety of people in different ways. And what's unique about these platforms is that they give us this capability to, with a scene camera, a camera embedded in the glasses or in the device, they give you the ability to see what someone else is experiencing as they go about their daily life. And some of these devices, like the SMI glasses shown here, also incorporate gaze tracking capabilities. So they can show you what someone is seeing, and also they can tell you what that person is attending to, where they're looking. So this is really a kind of new opportunity that these platforms have enabled for us to then begin to explore visual media in this new form. So there's a variety of applications that one could think about. So obviously these are mobile devices, so they provide context for mobile interactions. These devices give us the ability to understand a person's visual environment and to characterize what's going on in that environment. And then also these devices produce potentially very large records of visual media that you might want to exploit in some way through searching or skimming. And I'll touch on several of these different ideas in this talk. So here's a little picture that just illustrates some of the questions that you might be interested in asking and answering using these wearable cameras, using first-person vision. So you might want to know something about the environment the person is in, not just the GPS location, but actually the kind of the visual details. What kind of scene is it? Is it a beach scene? Is it an outdoor scene? You might want to know how the person got there, so they moved through their 3D world in some fashion, and we can get a lot of detail about that movement, the kind of terrain they walked over, for example, the change in elevation and the way it was distributed in time. And then you might want to know what the person is looking at, so what can they see in general, like maybe the beach in this case, and then what are they attending to. And then you might also want to know what they're doing. And each of these questions that I just briefly discussed here can be answered using technologies that come essentially from computer vision. So everything from recognizing objects to recognizing actions, mapping an environment in 3 dimensions from a sequence of images. All of these are computer vision technologies that have been developed in the past, and we can kind of further develop these technologies and specialize them to this particular scenario of a wearable camera or first-person vision. So in this talk, I'm going to give you kind of several examples of how computer vision methods have been adapted or developed for these different types of tasks. So here's the set of things we're going to discuss. So I want to talk to you a little bit about visual attention and about how it can be measured in these 3D kind of real-world scenarios, and then how we might use attention in a variety of ways, and also how we might, understand how to predict it even. I'm going to talk a bit about action recognition. So how can you take a video clip captured from this wearable camera and then label that clip in terms of what is the person's action? What are they actually doing in the scene? And then I'll talk about specific types of behaviors, namely social behaviors, and some work we're doing in understanding those behaviors in the context of autism. And then lastly, I'll talk about some techniques for handling sort of large video collections. So let's talk about visual attention. So this is really a kind of basic property of the visual system. Humans naturally coordinate their eyes with their body and their hands as they go about their daily life. This has been studied for at least a century using measurement devices. And the modern innovation really is the ability to measure attention in the field, in these naturalistic situations. And so there are some basic properties of the attentional system we'd like to discuss. And the main point for this part of the lecture is the fact that this wearable camera video is kind of unique in the sense that it basically gives you implicitly information about the attentional processes or the attentional system of the camera wearer. And you'll see an example of that shortly. So I just want to start by mentioning or acknowledging really some of the pioneering work in psychology that has established these relationships between attention and action. And Michael Land in particular is kind of famous for in the sort of late 90s, middle 90s, essentially wearing this very kind of uncomfortable looking device you see here and capturing some of the first data that related visual attention to action. And he studied, for example, how people's gaze was allocated when they were performing a variety of basic household tasks, like meal preparation, for example. And what he found, just one finding, is that, in fact, people often spent their time looking at the relevant objects during these tasks. And there's this sort of time course of looking that was characteristic of these types of actions. And we're essentially exploiting that observation in the work that I'll be showing you. And the difference is that we're actually developing an explicit computational model that can be used to perform detection or perform recognition. So here's an example of what one of these first-person vision systems produces. This is a video from the Aware Home Laboratory at Georgia Tech. And of course, you're seeing here what the student is experiencing visually, and the little pink donut shows you where they're attending. So they're going to make some kind of salad here, and you can see both what they're experiencing and where their attention is allocated. And so with this attentional cue, this ability to measure attention in real-world scenes, there are some basic questions you might ask. And the first question might be whether this gaze information, this gaze signal from the wearable camera, whether that's useful or not. And in particular, is it possibly useful for actually recognizing what a person is doing? So here's a little video clip. Take a look at this and see if you can tell by watching this video what the person in the scene is doing. So I'm sure everybody almost instantaneously recognizes what this is. If you didn't make a peanut butter and jelly sandwich in your life, then you may not be able to label this activity, but you can clearly describe, what the person is doing throughout this action. And of course, the way this video is created is we take the gaze measurement from the glasses, the center of attention essentially, and then we black out the entire video except for a small circle, 100 pixels around the point of gaze. And so the point of this video is to demonstrate that this point of gaze is very powerful. It's like kind of like a laser beam that just zooms right in to the part of this video that's important. And even though you can't see, 90% of the video, from the portion that's around the gaze, you can tell almost the entire story of what's going on. And so this suggests that gaze, if you have access to it, is in fact a very powerful cue for performing various types of action recognition. And we did some early work to exploit this a number of years ago. And in that work, we did a very simple experiment where we essentially built a feature vector that characterized the video clip. And the feature vector was constructed from the circle of pixels around the point of gaze. And here you can see on the right some labels of object names that come from some object detection system of the kind we talked about in my last lecture. And we're just essentially building a little descriptor here of each video frame based on the histogram of the object labels that occur within this circle of pixels. So this is a very crude feature just based on the co-occurrence of objects. And if we did this across the entire video, it would be very confusing because there's many objects that are present there that are not being used. But if we only do this inside the circle around the point of gaze, we actually get a very powerful feature that can be used for recognition. So this is one feature representation that's derived directly from gaze. And I should mention that in general in computer vision, one of the hardest challenges is actually figuring out in a large image or in a large video, what are the pixels that are actually relevant to the label. So this gaze kind of gives us this index almost directly to the relevant pixels. And we also use some features that are more standard kinds of color and texture features, and there's a kind of visual code book that's illustrated in a color coding scheme on the right here that just shows you some of those other visual features that we're using. So putting all these features together in a big vector, we're essentially concatenating the video clip into a series of frames and just stacking the features up from each frame to make a big feature vector, and then running a standard, in this case, a support vector machine classifier. And we get actually pretty good performance on this task, 47% kind of average accuracy. And really the important comparison here is that if we use some very standard, more classical action recognition features, we actually get a relatively poor performance in this video clip. So this just highlights that the gaze is actually much more valuable as a source of information than any of the kind of standard features you would have in kind of a more general computer vision setting. So this just points out that there's a lot of value in specializing the analysis to this first-person viewpoint. So that work, got us thinking about the value of gaze, and it led to a question of whether this relationship between gaze and action might go the other way. So if we only have access to the video clip, but the video clip has certain structure within it, could we actually exploit that structure to make predictions about the gaze? So this is now taking the video clip and asking, can we predict where somebody is going to be looking based on the video? And here's an example of the kind of video clip we're talking about. So again, this is a kind of meal preparation activity in the Aware Home Lab at Georgia Tech. And given this video, our goal is to produce the following output. Now, the green circle that you see is the kind of gold standard gaze measurement coming from the hardware and the glasses. And the little colorful bullseye that you see is the result of my student Yin Li's algorithm. And this algorithm uses only the pixels in the video and nothing else. So given only the pixels, we can make predictions about the gaze, and then we can compare those predictions to the measurement from the gold standard hardware. And you can see that the agreement is fairly close. So I want to just kind of show you now how we did this. What's the secret to getting these kinds of predictions? And kind of the high-level point here is that we're going to essentially be exploiting a series of features that really only make sense in this first-person context. So this is an analysis that you can do with these first-person videos that really wouldn't even make sense to do with other kinds of, for example, surveillance cameras. So this is kind of a unique solution to this particular domain. So here are the three features we use, and I'll just go through them with you one by one. The main point here is that we're not using any of the features you would typically think about. So we're not using any low-level visual saliency that, some patch of pixels, because of its contrast, might draw your attention. We're not using high-level information. We don't know what the activity is specifically. We don't know the objects that are involved for the purpose of this gaze prediction. So what we can use are these essentially egocentric or first-person features. And here's the first one, which is very basic. It's called the center prior. And the way you get it is you just take all the fixations in your gaze data set, and you fit a Gaussian to that fixation data. And if you do that with a kind of standard monitor-based eye tracker, like you see here on the right, then you get this very broad, sort of big Gaussian. If you repeat the same fitting process using the wearable glasses that contain the eye tracker you see here, then you get these center priors that are actually very compact. So you can notice a kind of striking difference between the real-world kind of center prior on the left and the laboratory center prior on the right. And the difference, of course, is that in the real world, you actually use your entire body to attend to the scene. So you orient your head, you orient your body first, actually, orient your head, then make small corrections with your eyes. So the gaze sort of perturbations you need to make to index the scene are much smaller in real life than they are when you're actually sitting in front of a monitor, being asked essentially not to move your head very much, and then using your eyes alone essentially to index the image. So there's sort of two consequences of this observation that are sort of immediate. One consequence is that if you just have the center prior, it's not a bad predictor. Especially in this wearable camera case, you can actually not do very badly by just saying that you're looking where the center prior is. So this suggests that wearable cameras alone with no eye trackers might actually be fairly interesting in terms of giving us access to where somebody is attending. That, of course, assumes that we can say something about how the camera is oriented in the world. And we talked in my lecture last time about many methods that could be used actually to track camera motion and identify where cameras are in the world. So you can think about the combination of those two methods might be very interesting. The second observation is that there's a lot of data about attention, which is essentially based on these monitor-based eye trackers. It may be worthwhile to go back and look at some of that work in light of this, these differences in real-world gaze behavior. So one place where the center prior is not very accurate is when you're making large gaze excursions. So here's an example. You're going to move a large distance. You make essentially a large jump, and your head orients, and your gaze corrects and catches up. Here you can see it again. There's a big jump in gaze. Your head orients to kind of center you, and then you catch up again. Here's a case where there's a strong relationship between head motion and the gaze displacement, or the gaze shift. And it turns out you can model that in a simple kind of linear rule that you see here. So the head velocity on the bottom is something we can measure from the video very easily using optical flow type techniques. And then once we know the head velocity, we can use that to predict how the gaze is going to shift relative to the center prior. So this is the second cue that we use. And the last one, which is actually the most important, is information about the hands. And what we do here is define essentially 4 scenarios where the hands are in different configurations that you can see here. And then for each configuration, we put down essentially a coordinate system that is attached to the hand and moves with it. And the idea is that, while the hand might move around within the field of view, the gaze is going to tend to be organized or allocated near the hands because, of course, you're using your hands to, to manipulate objects in the scene. All right, so that's the basic idea. Here's a density plot of the gaze distribution relative to these manipulation points, and you can see that it's a pretty nice compact cluster, suggesting that there is real value in kind of tying the gaze to the hands. So we put all of those cues together using a fairly standard architecture, a conditional random field to smooth the features in time. We treat the state of whether you're in a saccade or a fixation. These are some eye movement terms that refer to whether your eyes are actually stationary, kind of indexing the scene and doing perception, or whether you're shifting your gaze to a new location, which is what a saccade is doing. So we estimate that variable as a latent variable from the measurements, and then we use random forest classifiers to feed gaze predictions based on our features into this architecture. And so if you're familiar with the modern kind of deep learning revolution in computer vision and other areas, this is not a deep architecture. This is actually sort of a classical architecture. But for this problem, it actually performs quite well, and you can imagine kind of deepifying it if you'd like to do that. All right, and I'll just show you one more example then of how that plays out. So this is now another testing example of using this set of features that I described to do gaze prediction. So I think from an application point of view, this is a fairly interesting finding. It suggests that as these wearable cameras become more and more ubiquitous and easy to deploy, we don't have to settle for just having access to the field of view. At least for certain kinds of tasks, we can imagine knowing even more about where someone is actually attending, provided that we can do this analysis of the video and really access the content of the scene. And this is just showing you the results in the form of an ROC curve, quantitative results here. And really the main point of this is that if you notice this blue curve here, then this is actually the performance you get using just the center prior. Okay, so just the first cue that I showed you. And below that curve, which is the negative area, the place you don't want to be, are a lot of other methods down here that all use visual saliency. So visual saliency is just not very useful in real-world activities, and it's worth knowing that. And then up here are the methods that use the hand. So the dotted line here in red is using the hand, which is very powerful, and then smoothing everything in time gives you this final sort of curve. So this is a reasonable ROC curve, and you can sort of imagine doing additional work to make it better. And we have a data set that we use for some of these experiments, several data sets actually. We're working on a new one right now. And I just want to mention these are freely available if people want to download them and play around with these kinds of predicting attention or utilizing attention in the course of action recognition. All right, so that's kind of my kind of overview of visual attention and how it can be used. And I want to segue now and talk about action recognition. So I showed you one approach which exploits the gaze measurement, but in real life we're not going to probably assume that we have access to the gaze measurement. Now, based on the last finding, you might imagine you could just take the gaze prediction and then treat that as a gaze measurement and use that for recognition. And in fact, we tried that and it works pretty well. But as soon as you do that, what you realize is that really those cues we're using, the sort of head-hand cues, are probably powerful in their own right, and you should really just look at how to exploit them directly. And so I want to show you now some work on how we actually do that. And one way to think about a possible set of questions or goals here is we really want to understand more precisely how the first-person vision paradigm differs from these standard kind of third-person vision, like a surveillance camera kind of setting. And one obvious difference, which you can think of as having positive and negative consequences, is the presence of significant ego motion. So the positive side of having access to the ego motion is that you can tell how a person is moving through the scene, and you can tell how their head is being moved as they go about their daily life. So this access to head motion and in general to motion in 3D is a really powerful cue that we're already exploiting, for example, in our gaze prediction work. However, there's a negative, which is that when you're trying to use motion as a feature, when you're trying to understand what's happening based on the motion, then what you're getting in this first-person vision scenario, as we talked a little bit about last time, is that you're getting the mixture between the head motion, which is happening because of the camera wearer, and the motion in the scene that's coming from the activity. So think about someone waving their hand at you. If you're waving your head at the same time, you're going to see a mixture of your head motion and their hand motion. And that could be potentially confusing if you're trying to use those motion features for recognition. So there's a basic question of, are motion features useful for recognition in this first-person vision context? And if so, how should we exploit them? And then we also know from some kind of previous work in the field, and a lot of work in vision actually, that objects are also really useful. If I know what objects you're manipulating, I can say something about what you're likely to be doing. And so we'd like to understand what that story is, as well. So I'll talk about a study we did to shed some light on those things in just a second. And really the main take-home point from this section is that we have these additional cues from the first-person setting, the head motion, the hand pose, and perhaps additional information about gaze. And you can think of these cues as really just extra pieces of information that we have access to because of this first-person vision setting. And so what we're going to show you is how those kind of relate to each other and what their value is. So this is a paper that appeared this year at CVPR, and we essentially studied the combination of kind of classic motion features and object features with these particular egocentric features, and did a benchmark study to see what was the value of these features in a standard kind of action recognition problem. All right, so just to give you a quick overview of the features that are involved, these are the motion features that are typically used in action recognition. And so then the question is, how do those features behave? First of all, how are they constructed? And then how do they behave in the first-person vision context? So let's have a look at that. So here's an example of the kind of outputs you get. So you get the video sequence, you track points shown down here, you calculate some spatial features like this one, for example, you calculate features from the motion itself, and then the question is how to handle the camera motion. And this question arises in a lot of settings, so it's been studied in kind of the general literature as well. And one very successful approach from Cordelia Schmid's group here is to essentially track the motion over time and then try to stabilize the video by correcting for the camera motion. And then once you've done that, you can try to identify which pixels or which motions are different from the background, and those are likely to be really important parts of the scene. So here, for example, you can see there's kind of this overall kind of looming pattern of motion here in the background in white, and then in green are some people probably walking towards the camera who are, moving differently from the background, and we can successfully separate the people from the background using this motion modeling technique. And so there's several examples here where it works, and there's some examples where it fails. And one way to think about the failure case here is that if the camera motion is really large, then you tend to have trouble explaining it with a simple model. In this case, they're using a homography model, which is somewhat simple. And you're also likely to get a lot of motion blur, which makes it harder to resolve the features that are going to be used to do the matching. So there's a number of kind of technical challenges here that arise because of this, essentially large motions of the wearable cameras. Let me just show you this representation so you can get a sense of what it looks like. This is the particular couple of movie clips. Basically, you can see on the top is the kind of the dense trajectories that show the motion over time, and then in the middle and the bottom you can see the kind of motion-derived features. And the nice thing is these features tend to pick up the motion structure in the scene, but you can see that it's not just the actor or the objects; it's actually the entire scene shows up because there's so much motion going on. So we tried this kind of basic technique here in our first-person vision setting, and it didn't work actually that well. And then we began to look at the problem, and then ultimately my student Yin Li came up with a solution. So the main problem here is that the previous approaches assume that you can really compensate in a strong way for the camera motion. And that turns out to be much harder to do when the camera's being worn on your head. And one way to think about that difference is that when you're capturing a video for YouTube or for the web, you're really kind of doing your best to keep the video stable, to kind of keep the camera on the action. So you're trying not to introduce extraneous motions of the camera. But if you're wearing the camera and going about your daily life, you're not thinking about being a filmmaker. You're thinking about just doing what you're doing. And the camera then, in that case, is just going to experience, in general, much greater motion, because it's really, your head is being used to do something in the world, not just to capture some pictures. And so we have to live with that, difference, and then that in turn affects the way we think about, the analysis. Okay, so then just to now kind of cut to the punchline here, I want to show you how we actually did this analysis, and then you can just see here a couple of experimental results. So we have a new approach essentially to doing motion compensation, and the details. Let me just, I guess, highlight the details real quickly. So the main difference in our approach is that we don't do this large-scale frame warping, which is done in the previous method, and the reason is that it just doesn't work very well in these large camera motion cases. We use some features that are a little more efficient to speed up the matching as well, and this makes the overall approach more efficient computationally. All right, so here are some kind of findings here on our data set. And the way to think about these is that we're going to essentially take 3 data sets that contain different combinations of activities and objects and actions, and we're going to look, on the one hand, in the state of the art, which would mean applying kind of the baseline methods that I was talking about that are not adapted to the first-person vision setting. And so we're going to first kind of look at what happens if you just use kind of state-of-the-art methods, and what happens if you actually compensate them for the motion. So what you can see here is that in these kind of standard data sets we have here, we get some boost here by using the motion-compensated visual features. And then we're going to ask the question, now what if we also add the object information in there as well? So we know that object cues in general are quite useful in action recognition, and we see that in every scenario, the object cues give us a boost. So this kind of tells us, in terms of thinking about the value of different features, this tells us that motion, it can be very useful, and if we can compensate motion using the information we have about the wearable camera, then those motion features add real value. But adding information about objects gives additional value that is not satisfied or captured by the motion features alone. And now we can look at adding to these kind of baseline motion feature plus object cues. We can now consider adding all the other cues that come from first-person vision, from the head, hand, and center prior, a source of information. And so you can see here, the main finding here is that if we put all of our features together, then we get this purple or kind of dark blue bar you can see right here with my mouse, and that's significantly higher than the previous bars we had from those other baselines. So just motion compensating standard features is not enough. Adding the egocentric features really gives you a big boost. And then in this data set, if you add, in addition to this, actual gaze measurements from the hardware and the glasses, you get another boost, which is significant. But in this other data set that we have, which differs in some details about how it was captured, actually adding the gaze doesn't actually help a whole lot. So I would say the story here is still a little bit unclear as far as what is the value, what is the precise value of actual gaze measurements. We have some data sets where adding actual measurements of gaze is helpful, other data set where it seems to help us less. The caveat with some of these findings is that the data set sizes are still really too small, I would say, to have a very strong support for these claims. So we really want to expand these data sets and incorporate other types of activities of daily living, and then see if this pattern kind of holds across a larger set of data sets. But these results are suggestive. If this pattern holds, the one right here for this Gaze Plus data set, then that might suggest that, in fact, we don't necessarily need the gaze hardware, the hardware for actually tracking eye movement, for this, specific task of predicting what action you're performing during hand-eye coordination. And one caveat that I want to emphasize again is that these features we're talking about adding here, the first-person vision features, we're talking about scenarios where the action involves a significant amount of hand-eye coordination, like cooking a meal where you're manipulating objects. And we wouldn't expect those features to be valuable, essentially, in other contexts where your hands don't play a major role. So in social interactions where you're really talking and looking, it may be that your hand features are not that important. Or when you're driving, the hands tend to be on the steering wheel most of the time. They're probably not that important in predicting where you're going to look. So to really get a broad coverage here, we need to actually think about what are the scenarios in which people are coordinating their gaze, and how can we think about modeling attention in each of those scenarios. And we're doing some work on that now in my group, looking at some other scenarios besides the hand-eye coordination case. All right, so I want to move on now. We're kind of making a transition here from in some ways, very basic and kind of low-level behaviors, where you're looking, what your action is, and we're going to try to move now towards some more high-level constructs, some more complex behavioral pictures that we can put together using these methods. And I'm going to really be focusing for the last half of my talk on social behaviors. And these are some areas where I think you can get access to very interesting kind of high-level cues using these same tools. And I'm going to start by talking about some work we're doing in the context of understanding autism and providing some technologies that might support individuals with autism. So I'll give you some overview of that, sort of the autism domain, and then it'll turn out that again, visual attention plays an important role, and we have some work on eye contact that I'll show you about that we've been pursuing. All right, so just a quick kind of overview here of the autism domain, just in case you haven't seen very much about this condition in the past. So it's a brain disorder with a genetic underpinning, but no biological markers, so there's no blood test for autism. And individuals with autism show differences in development at a very young age, and in comparison to a typically developing cohort. And those developmental differences result in time in significant challenges in developing social relationships. So kids with autism have much more challenges than typical kids in forming, basic social bonds with their parents. A significant number of children fail to develop language, spoken language, and intellectual disability is also a co-occurring condition in about half the individuals. But it is a spectrum disorder. I'm sure you've heard of the autism spectrum, and so the kind of the distribution of these different challenges varies widely across the affected individuals. And this is a relatively modern condition in the sense that it was first described in 1940s, so relatively recently. There hasn't been a lot of time yet to really study autism relative to other conditions. But for our purposes, there's actually two aspects of autism that are really critical, and they both these observations come from the fact that autism is behaviorally defined. So if you want to know if a child is at risk for autism, you have to have an expert clinician observe their behavior. And that behavioral observation, which is done in the context of a standardized instrument, where you essentially interact with the child in a structured way and look at how the child responds to the interaction, that's a critical piece of evidence for making a diagnosis. And then once you have a diagnosis, then the immediate step is to get treatment. And the good news about autism is that there are now essentially very effective treatments that, especially when delivered at a young age, can have a significant impact on outcomes in some children. And in fact, some children will lose their diagnostic, they'll fail to meet diagnostic criteria as they get older. So the jury is kind of still out about exactly what happens with these individuals because there hasn't been enough time to really study it yet. But it's certainly very optimistic around autism being treatable. The challenge, though, is that these treatments involve essentially one-on-one behavioral interactions in the form of interventions. So they're very labor-intensive, involving an expert therapist working with a child. So in this setting, it turns out that behavior is kind of the key property or the key quantity, if you will, to measure. And one of the motivations for this work was the observation that it's very hard to measure behavior in these social settings in a kind of inobtrusive way that's more automatic. And automatic measurement is critical, of course, so that this could scale up and actually be applied to the entire population. And the motivation for autism coming from the public health point of view is really coming from its prevalence, which you can see here is kind of an old plot actually that I have. But the latest numbers as of last year are a prevalence of 1 in 68 of all children in the U.S., 1 in 42 in boys. And these are large numbers, and they make public health systems very nervous, and so that's been kind of a big motivator for the influx of attention and funding to look at autism. So there's a lot of reasons why this condition is worth studying. So one of our goals is to develop a kind of very general capability for looking at these kinds of behavioral conditions, and we refer to this as behavioral imaging. And the idea is to make an analogy to the way that medical imaging has transformed the practice of medicine over the last 100 years, giving us this kind of unprecedented ability to quantify states of disease that were previously you only could study them qualitatively. And likewise, we want to develop for behavior the ability to quantify behaviors, measure them precisely, and then ultimately be able to understand behaviors as objective phenomenon that evolve in time and can be modeled and studied. And so you can see some possible goals here for this technology. And so we were able to get some support from the National Science Foundation a number of years ago in an expedition project that's just about to end. And you can see our team here covering many universities in the U.S. And this was really the first kind of large-scale effort to look at the development of a variety of technologies, computer science and engineering technologies, that were ultimately targeting the study of developmental conditions such as autism. And so one of the consequences of this large-scale study was we actually built a lab at Georgia Tech, and this is my colleague Agata Rozga, who really was the instrument behind building this lab and getting our program set up around autism. And you can see here, it looks a lot like a kind of child psychology lab if you've seen those labs before. But it has, in addition to the usual kind of children's furniture and toys and so on, it has also a ton of different instruments. So cameras of various types, some wearable sensors you can see here you can put on the child, microphones in the ceiling, microphone on the child as well. This is a little vest where you can actually record audio from the child. So this gives us a nice kind of cross-section of different signals, video, audio, wearable sensors. And the question then is, can we use these signals to actually analyze and understand these social behaviors and ultimately develop some tools that could be deployed in a clinical setting, for example, to improve the standard of care for autism. And so we spent actually a lot of time in this project trying to figure out what the right role was for these technologies. So you can think of this as a kind of a killer app question. What's the killer app for computer science technology and studying children's behavior? Or you can think of it as the question of just what's the right target? What is the problem which is really critical, and the problem for which our technology is really the most compelling solution. And so after quite a bit of time, we kind of hit on a couple of things that I think are salient. And one observation was this motivation that one of the things that's impacted very strongly in autism is gaze. And so in fact, this eye-to-eye gaze, known as eye contact, is a key social measure, and there's a long literature going back a number of years that tells us that in kids with autism, gaze is perturbed away from the typical pattern, and eye-to-eye contact is impaired. So you may have heard that kids with autism don't make eye contact, and while that's a gross generalization, there is a sense in which it's true that there is this strong difference in patterns of looking that are associated with autism. And so the reason this is important is that we really think that one of the main roles for this technology is in looking at treatment. And when you talk about treatment, you're talking about providing a behavioral intervention. And one of the main things that you immediately worry about is whether that intervention is working. And so this concept of what's called treatment response, whether a child is a responder or a non-responder to a particular treatment, that's a key thing to understand. And there's a lot of different behavioral interventions, and there are obviously, a lot of different places that you can get therapy from. And so for a parent with a child, whether the child is responding to treatment or not is a key question. And they might, look at that question, look at the answer to that question, and decide whether to, to change the treatment regime, to try a different care provider. There's lots of ways this impacts the parent's life. And the care providers want to understand whether their treatments are working or not. And this is a really challenging thing to understand. And one thing that you look at, that you notice when you look at this literature, is that a kind of outcomes related to gaze, whether the eye contact is an actual treatment target, that you're trying to improve eye contact as part of your treatment, or whether eye contact is implicitly involved in other outcome variables. So, for example, social initiation is trying to get the child to initiate social interactions more frequently, and those initiations often involve eye contact. You catch somebody's eye and then interact with them. And so this notion of how the child is allocating their attention during these naturalistic face-to-face settings turns out to be really important in understanding if therapy is working. And that seems like a really nice sweet spot in the autism space for technology, because it's an area where there's just really no consensus right now in the research community. So a recent study of instruments for measuring treatment response found a large number of instruments, the majority of which were used only once, which means that there's no agreement yet about how you should measure these responses. So we really took that to heart and began to develop some technology that could be ultimately used to assess one dimension of treatment response, which is this dimension of eye contact. And so that's now I've motivated why eye contact is important in autism and why it might be a good target for a computational investment of resources in terms of its importance. And now I want to talk about why computational technology really is needed, that this is actually a construct, a variable that's very hard to measure in any other way. So in kind of clinical settings, there really is no precise quantification of eye contact. It's just too difficult when you're one-on-one with a child to keep track of when they're looking at you and you're trying to interact with them and engage them. It's just too difficult for humans to do that. And so therapists in a clinical setting give very qualitative assessments. They'll get a rough idea of how much eye contact they got, but it tends to be not very precise and possibly biased or affected by a lot of subject variations. In research settings, you can measure eye contact, but it's done by essentially human labor. So undergrads have to look at images like this and then decide in this image, is the child making eye contact or not? And this is a very difficult assessment to make, even for a human. So there's a real need for technology to solve this problem. And I just want to briefly run through a procedure that we developed in my group. This is the work of my master's student, Zhefan Ye. And so this is a kind of particular platform we use. It's called Pivot Head. It's got a camera right here. It's essentially a wearable video recorder. And we put that on the examiner or the clinician in this setting. So the child is completely unencumbered. The child has no hardware on them at all. And the examiner wears the glasses with the camera. And then because the examiner is wearing the camera and they're interacting in a face-to-face setting with the child, they just naturally bring the camera to the child. They bring the camera near where the child is, and you get these beautiful images where the child is, in this case, making eye contact. They're oriented toward the camera. They're looking toward the camera because they're looking at the eyes of the examiner. And then you can imagine that you could analyze these images with a program to essentially determine whether or not the child is looking in this direction. And if they are, then you've got a moment of eye contact you've detected. So that's the approach we follow, and I'll show you the details here in just a second. But I just want to make a point that even if you don't do automatic analysis, having these sensors in the right locations can really be helpful. So here's an example of this is some work we did with Wendy Stone's group at UW. This is some head camera versus room camera shots for a child. And even for a human, it's much easier to tell what's going on if you have access to the wearable camera video. All right, so I've explained the basic idea here already. We're just going to analyze these images using computer vision techniques. We're going to find the face, find the eye regions, track the head over time and get its 3D pose, and then we're going to localize the direction the eye is looking at through some pattern recognition analysis. I won't go into all the details here in the interest of time, but the main point I want to make is that you really have to think about this problem holistically. So it's not enough to just look at the eye region alone. This is a well-known phenomenon, and so you can see from the sketch up here, what people are doing is they're actually taking the whole face into account. They're using the nose essentially to localize the pose of the head, and then they can interpret the eye region appropriately in that context to tell where they're looking. So these images all look the same essentially, many of them, but if you can see the actual entire image, and then as a human you're inferring the pose of the head, then you can tell whether or not the child is looking toward you or away. So the point is just that you have to really do this at the head level. It's not enough to just look at the eyes. And so we do that using some software that tracks the face and then localizes the head in 3D and then analyzes the eye regions. And so I'm just going to show you the result of the method here without going into all the details. And the way this video works is that you're going to see the child playing with the toy. The examiner, of course, is wearing the camera, and you're seeing the examiner's view of the child here. And then the examiner is actually trying to get the child's attention. So over time, the examiner will, get the child's attention. The child will look up, and then in those moments, you'll actually see eye contact, and the algorithm will slow the video down whenever it detects a moment of eye contact. So you can tell by watching whether it's working or not. So it's just playing here. Here's your first eye contact moment. So the video is slowed down. The green box says that it was detected by the algorithm. Now she plays some more, a little faster, and now again, another moment of eye contact. She plays some more, and so on. So I think, the story here at a high level, I think, is probably very familiar to folks that are, involved in mobile health types of applications. We're really getting the same kind of solution in this context, which is that we want a technology solution which is really inobtrusive. We just insert this camera into the interaction. We insert it in a way that doesn't change the interaction at all. And we've actually quantified in some studies with Wendy's lab that having the examiner wear this particular brand of glasses has no effect on the child's behavior. So there's no reactivity here. The child is doing the same thing they would do without the camera. And now, because the camera's been inserted, we get this kind of very powerful data about this particular behavior. And then the analysis can be done completely automatically in this case. And so from a clinician's point of view, this becomes a device that you can wear to measure and quantify a particular social behavior. So when this is finally, let's say ready for clinical application, then we'll essentially package this as a system where you would just wear the glasses. At the end of the day, you would download the video, the program would run, find the frequency and the duration of these moments of eye contact, and that now becomes an objective measurement of the treatment of this individual that you can then add to a clinical record. You can use it to try to refine the treatment. You can figure out what things are working and what things are not. And it becomes a very potentially powerful tool for understanding how the child is responding to the intervention. And then you can imagine, kind of building on this to look at other social behaviors besides eye contact and try to expand the portfolio of measures that are available through this same approach. And so here I just want to show you the kind of ROC, the precision recall curve actually in this case, and you can see that there's a lot of variability. This is actually done with our initial data set that we collected at Georgia Tech in our child study lab, and you can see that for some kids it's actually working pretty well, the kids up here, and for some kids it's actually not working well at all, the kids down here. And the average is not bad. This operating point here is essentially the inter-rater agreement. So this is the extent to which the human coders who produced the ground truth for this study, it's measuring how well they agree with each other. And of course they agree quite well, and they provide kind of the gold standard measure for what's happening. And so there's still quite some gap here that we need to close to go from where we are now up to this dot. So there's still some work to do, but these are, I would say, promising results, and they make us optimistic that if we keep pushing on this, we will in fact be able to develop some really useful measures for these key kind of social constructs. And I just want to mention how we're pursuing this going forward. So we have a relationship with the Marcus Autism Center here in Atlanta, which is a major autism center in the Southeast. And we're working with Caitlin Delft in the Language and Learning Clinic. And we're doing some pilot study right now where we're putting the pivot head glasses on the clinicians at Marcus in some controlled, some pilot settings. And then we're going to see essentially how well the technology works in an actual clinical setting when the folks wearing the glasses are not our kind of highly trained research staff, but are clinicians doing their job. So this will be very useful, I think, in understanding how close this is to be widely usable, and we should have some story about that by the end of the year. So I just want to close by showing one more application, which is kind of interesting, which is really this issue of how you skim video collections. So video collections are coming, and probably the most practical source for this are these body cams that are now in the news and are going to become more and more widespread. It's almost a certainty. And then you're going to produce these huge corpora of wearable camera videos that you need to somehow consume and analyze. And it's really a challenging task right now to think of what you would do with 500,000 body cam videos taken over the course of a year from a small police force. And I just here I'm listing a couple of kind of very standard techniques from the literature for how you might handle large video collections. And there's many ideas of what you might want to do to get information out of this type of media. And the three popular topics here are summarization, skimming, and searching, and they represent different trade-offs as far as how the analysis is used. So summarization is really about telling a story, distilling the video down to a much shorter video that has somehow the same content. It's a really nice idea. One advantage is that if it works, you can actually scale the size, so you can kind of scale the summary to the time you have available to watch it. But the con of this kind of approach is that you don't know what you're missing. So if the summarization algorithm leaves out something because it doesn't think it's important, then you'll never know it unless you go back and watch the video. Searching actually has a similar story, although with searching, if it's interactive, you might eventually be able to find something if you search long enough. But these are also very efficient. You only see the things that you're searching for if it's working well. But right now, I think one of the more attractive approaches in terms of just being able to access information easily is actually skimming, so just quickly going through the video at a high speed. The advantage of that is that it's a lot more robust, so if you miss something with your algorithm, you still may actually see it in your skim. And then, of course, the con is it might be less efficient because you're spending time still looking at things at high speed you don't care about. It's actually worth talking about all these methods, but in the interest of time, I'm just going to focus in on skimming as being one example that I think is kind of interesting. And we're seeing now a number of interesting technologies to support the skimming action. So here's a way to think about it, and I'm going to kind of show you two approaches essentially from the literature, and then we'll conclude. So the basic idea of skimming is time-lapse. And time-lapse you're probably all familiar with. You take a long video and you just drop frames. So you see a building being constructed, and the video is captured over the course of a week, and you drop, you limit it to one frame every hour. Or something like that, and then you get, the building going up in the course of, 10 minutes. And so you're distilling this very long temporal record down to a much shorter temporal record by simply dropping frames. And the nice thing about that is that the frame dropping is kind of uniform in time, and so you're less likely to miss something. Of course, if it's really short in time and it's important, you might still miss it. But it's probably the least biased in some sense of all these ways of compressing down a large collection of videos. Now, there's an actual problem with this approach. So this is a very common approach, actually, and it's really a pretty good idea. But there's a big problem with it in the case of egocentric or first-person video. And the problem is that in those cases, as we know from the lectures we've had, conversation we've had, the camera motion is extreme. Now, what's interesting is that when you're wearing the camera, of course, your eyes are in motion just like the camera is. But you don't notice any of that jerkiness or vibration or excursion of the camera because, of course, your brain is already compensated for the camera motion because it knows how your head is moving. So as an observer in the scene, this camera motion, these artifacts of being jerky or whatever, are just not visible to you at all. You don't perceive them. But when the video has been captured and you're watching it offline, then you no longer have that feedback from your body. And so you don't have this perceptive signal that compensates, and then you notice all the jerks and bounces in the camera. And these videos can really be unwatchable, especially at high speeds. They can sometimes be unwatchable at regular speed. At high speed, they're really unwatchable. But there's a very nice piece of work from Microsoft that Michael Cohen has been involved in the last 2 years that produced a really nice technology which is addressing this problem of hyperlapse, which is really about how you drop frames and simultaneously stabilize the video so you don't have these artifacts due to the camera motion. So I'll briefly highlight that work for you. You can get a sense of what it's doing. And then I'll talk about some related work, not that related, but in the same vein, in my lab by Alireza Fathi, looking at how you might detect social interactions and then use them to produce a kind of skim that is kind of highlighting the social interactions you care about. So let's just look at these results. So I'll just really take you quickly through the hyperlapse idea. The paper was linked to this lecture, so you can go look at the details yourself. But here's the basic idea. The subject in this case is wearing the camera and walking. Because they're walking, as you may know, their head is moving kind of up and down, and this blue dotted curve here in this graphic on the left is tracing the motion of the camera over time, and you can see these vertical excursions of the camera. And these make it very hard to watch this video as a third person watching it, especially at high speed. Now, if you do regular time lapse, you're regularly sampling in time, and you can see that the time lapse video, which is the black curve, has essentially the same motion as the blue one. So it's faithful to the motion, but as a result, those artifacts remain and in fact are even exaggerated in the time lapse. You can see that the frequency in some sense might even be higher depending on how this is done. And then what you see in magenta here is the result of their method, which is a very clever idea that essentially does time lapse but adjusts the frames that you sample based on the motion. So you're no longer sampling regularly in time. You're picking actually sample times with the property that they tend to minimize the excursions of the camera. So the camera follows a much smoother path here than it does in the other two cases because you've optimized for that path in doing in forming the video. And this is done computationally by building an energy function which essentially matches each frame in the video to nearby frames. So this banded matrix is the result of searching in a temporal window in the video. And then you're essentially doing some dynamic programming to optimize an energy function that's shown here in a false color. And the energy function is essentially a trade-off between the amount of frame-to-frame registration or alignment in the video. So you're trying to find frames that are well matched so you can maintain a kind of continuity in terms of the visual appearance of the scene so it doesn't suddenly jump from one thing to the other. That's one term in the energy function. And the second term is actually just the motion. So you might find a very good match in terms of a kind of a similar scene, but then the motion might actually be large, which could lead to jerks. So then you kind of trade off those two terms to produce the final result. So I want to show you their video. Unfortunately, I couldn't get it to embed, so I'm going to quickly switch to my browser here and just show it to you from their website. And I've already got it queued up here. So hopefully you can see the video. So this is going to show you, when I play it, it's going to show you on the left kind of just a time lapse, which is really going to look bad. And then in the middle is actually a kind of earlier hyperlapse algorithm, which is also doing registration and time lapse. And then finally on the right is the method of the authors. You can see the authors up here, and this is their website, which is linked from the content. So let me just show you this real quick and get a sense. And I'll turn off the sound here as well. Okay, so basically you can see that on the left, you really can hardly watch the thing. On the right, it actually looks pretty smooth. And I'll just give you another example or two here. Let me just go forward here and give you something else. Let's have a look at that. So that's another example. This is comparing it to an Instagram. Have their own version of kind of this hyperlapse, and there's some qualitative differences there. There's also this kind of interesting thing you might have seen. It's kind of a hyperlapse selfie, so you're kind of looking at yourself as you move through the scene, and they're claiming that this thing looks a lot better than the one on the left. So you can just get a sense that, the nice thing about this is I think this is a really nice tool that we can now think about capturing these large video collections from wearable cameras, and we really can skim them. We can just speed up and change the speed and kind of go through and find things of interest. So for a consumer who's accessing their own video, this might be a very useful tool for actually exploring what they've done throughout the day or finding a moment of interest. Okay, so now I'm going to conclude by just showing you one more approach, which is based on a different idea of actually kind of modeling some specific social patterns of interest and then using the model to find moments within a large video record. This is the work of my student, Alireza, in the front here. This was done when he was an intern at the Disney Lab in Pittsburgh with Jessica Hodgins. And the basic idea is very simple. So we want to take a scene like this, and then we want to figure out where is everybody looking. So we want to get at these kind of social interactions that are ultimately mediated by, again, by the orientation of the head and by looking. And so in this case, we can actually find all the faces in the scene pretty well. We can estimate the orientation of those faces using computer vision methods. And then what we're going to do is we're going to turn this image that you see here into a 3D layout, a kind of bird's eye view of the scene, where you can tell where the attention is being allocated in a kind of group sense. And so how can you go from this image to a 3D layout? Well, if you remember the last lecture, there's a number of tricks we can use. So one thing we can do is we can actually calibrate the intrinsic parameters of the camera. So we talked about that. And what that lets us do is it lets us associate with each of these faces a ray in the scene that backs that face out along some line. So this is the basic projection from 3D to 2D that we talked about last time. And then once you've got that, you know you have an index of where out into the scene the person is located, but you don't know where they are along the ray. But if you know the size of the face in general, and you know the size of the face in the image, you can then estimate that distance by just looking at how much the face has been essentially shrunk or expanded by the perspective process. So that process lets us build this kind of layout here. And then we do some additional filtering with a Markov random field to identify where people might be looking. So we have this hypothesis that people are more likely to look at other people at the same object rather than different objects. And we can build this color-coded layout where you can see here that these blue people are all kind of looking at the magenta person. These cyan people are looking at the yellow person who's the first person, and so on. This is not very precise. The geometry here is inaccurate, but it gives us a qualitative layout. And we can then look at this layout over time and identify different categories of social interactions. Here you can see on the right of this slide some categories of interaction, whether there's a monologue, one person talking, whether there's a discussion, multiple people talking, and so on. And what we're going to do is simply run our filter over this video, analyze the faces in every frame using the procedure I just described, and then pull out the particular patterns of interest and highlight them. And so here's, again, a kind of skimming of Disney World. This is Disney World at high speed. And then whenever the system finds a moment of interest, a social interaction, then it slows the video down so you can see that particular moment and identify it. So here's one moment that was detected in the video on the bus, a dialogue on the bus, and then you'll see another example here of what's called a walk dialogue. They're walking side by side and talking. That's a very characteristic pattern of motion in the video. So this becomes a tool for skimming, but here using a little different criteria, looking at the social interactions in particular. All right, so with that, I want to just kind of wrap things up, and I'll just show you one quick idea where we're going with some things. This is actually work in the MD2K program by my student Alicia Barger. This is about looking for TVs, so another thing we want to do is identify TV watching behaviors, and there's a variety of reasons why that could be interesting. So this is some preliminary results of finding TVs in these first-person videos that we're kind of working on right now at Georgia Tech, and we'll have more to say about this as we get more results going forward. So just to conclude, I've gone over a bunch of territory here. I just want to kind of point out the highlights. So I think this first-person video is very interesting because it implicitly encodes the attention of the user. We have talked about gaze in this setting, and it's a very powerful cue. And interestingly enough, it can be predicted often during these hand-eye coordination tasks. And because of the nature of this wearable camera, there are features that don't exist anywhere else. And those features are really valuable. We combine them with kind of standard action recognition features, we get a significant boost in performance of our methods. And then there are some very specific applications to eye contact, to skimming, that really stem from our ability to build kind of very specific models of social constructs and then detect them in these first-person videos. And with that, I'll conclude. Thank you.
Thank you very much, Dr. Ray. Any questions for Dr. Ray?
I have one, Jim.
Sure, go ahead.
How do your algorithms deal with, I guess, more complex background motion in your videos? I see how they deal with the camera motion, but if you had a more complicated background, something moving, how do you handle that?
Yeah, you're absolutely right. So, you can think about, what's like the worst case scenario, and I think if you're kind of, you're walking and then a big bus is going by, and then between you and the bus is, someone that you're talking to, and now your job is to determine, what's happening, let's say, socially in that setting. So you're absolutely right. You got the, the motion of the camera, you got the motion of the bus, and in that huge, signal, you're trying to pull out, let's say, some nod of the head, by your colleague. So that's a very challenging problem. I don't have any really obvious solution to give you. I think everybody has trouble with that case. Our method is kind of already in some ways kind of giving up on actually modeling the camera motion. So we're really just trying to find an overall motion pattern. But that doesn't mean we couldn't be distracted by the same mixture of components. So I think that the only way to really, ultimately address that problem is to have a model which is much more complex. So if you think about performing these kind of analyses not in the 2D, video world, but actually in 3D. So actually localizing the camera in 3D, then, talking about where are you attending relative to the 3D scene, which you might be able to reconstruct using structure from motion types of ideas. In that setting, you might be able to then handle the moving objects and figure out, there's this other motion that's really significant. But the unfortunate issue is that, those algorithms also have trouble when there are large kind of dynamic elements in the scene. So this is not a easy problem to solve. But I think it's the case that those type of large background motions, they're actually a little bit distracting for people as well. So if you were, having a conversation with your friend and then giant trucks were driving by every few minutes behind them, you might ask them, could we just come over here and talk, instead? So I think for people, these can be distracting as well. They're obviously much more distracting to our algorithms. But I think what we'll find is that people don't tend to, naturally gravitate towards those kind of situations when they're doing interaction. So there may be particular, niche markets like maybe mining applications where, this could be a real problem. But I think other applications, it's certainly going to happen, and when it happens, we won't be able to get data, for example, right now. But I don't think it's going to happen all the time. And that's probably the, what we're hoping for right now.
Thank you.
Jim, can you hear me?
Yes, Santosh.
So one question from a user perspective.
Yes.
This all sounds quite complicated and quite complex. So how hopeful should people be about being able to have a usable, reliable model for detecting cues, let's say, for a smoking cessation?
Yeah, so I think that's a good question, and let me answer by way of analogy. So in the in the 70s and 80s, industrial automation was becoming really important as a technology, and at that point the computer vision technology was in a very preliminary state and really not suitable for most applications. But because of the the real need for those kinds of technologies, there was an incentive essentially to really develop very specialized technologies for let's say product inspection that were really designed to work in those factory environments. And so I think if you look at the state of general computer vision at that time, you might be pessimistic about was it really going to be useful. But when you then went and actually studied the specific applications in great detail and developed methods that were really tailored to those applications, then it turned out you could make progress, and people actually did build very impressive working systems even at that time. So that's the analogy that motivates me. I think we really haven't as a community in computer vision spent really any time at all thinking about kind of real world behaviors and how they could be measured with cameras and how they could be utilized in specific medical settings. And so I think that if you, as we're doing, and I think other people are interested in this as well, as you begin to do that, then you sort of discover ways to, essentially deal with the ambiguity and the uncertainty to, try to compensate for the challenges. And so I think that's a way to make, forward progress. And just to kind of highlight, again, kind of the things that are working. So the eye contact is a great example because, faces are actually pretty easy to work with right now. I showed you a couple of examples where we really treated the problem of detecting the face, estimating the orientation of the face. We really treated that as as kind of a black box, commodity technology, which is not to say that it doesn't fail sometimes, but it works well enough that you can build things on top of it. And so I think that's going to be part of the strategy here, is to really figure out those particular applications where the cue is really important and valuable, and the way it's manifest in the video is such that we can actually build a reliable solution. So it took us a while in my expedition to get to eye contact as something we would work on, and to then realize, its value. But now I feel like we have a handle there on something which is useful, and we can make progress, with a practical system. So I would hope for the same thing in MD2K, that we'll actually, identify these very practical scenarios and then specialize our methods for them as a way of making progress. So I'm optimistic, in spite of the complexity, but I do think it'll take some time.
Thank you. So let me ask one more.
Okay, go ahead, Santosh.
So what is the impact of the battery life on this?
Yeah.
The issue is that wearing something in eyeglasses, that means the battery can't be conspicuous, it can't be heavy, right? So we are talking about lightweight batteries, potentially, those batteries which are used in the earplugs, right? Or
Sure.
for those who have hearing problems, so those that are used in hearing aid, that kind of battery. So we have very tiny battery, and
Yeah.
and then we have to capture the video, then do the processing, right? So
Right.
I'm just thinking about the real life utility. So how do these constraints of wearability and usability in the real life environment affect the modeling process or the reliability of detection itself?
Yeah, that's a great question. And I would say that, right now, in terms of the research community, I don't think there's really been a lot of work done. I mean, you can definitely find some work, but by and large, I didn't really talk about battery life at all in this talk, and that's because right now the focus in the community has been largely on, can we solve the problem, and we haven't really made an investment yet in figuring out what the power constraint means, for the solution. But I think that, I definitely think that there's room to make some progress there, and I think there are some fairly, straightforward solutions that we can think about. Now, whether they will actually work in practice remains to be seen. But one thing that we might, imagine is that right now the video we're capturing is not really informed by the task we're solving, and that's fine, because we're using a general purpose imager. So then, we're just going to capture the video that's there, and then we're going to exploit it. But certainly, if you cared a lot about these issues, one of the strategies you might follow is to figure out, what exactly do I need to sense in order to make the determination I need to make. So if you're talking about a very specific, task like finding a face and so on, then there may actually be, additional kind of corners you could cut, in order to really be conservative of power. So for example, maybe there's a pattern of a face at very low resolution, which is still discriminative. So you might, imagine that your camera, again, how this maps onto hardware technology is not clear to me, but imagine that you have some way to sort of, only kind of image in certain pixel locations or in a certain way that, you can use to conserve power. So maybe you capture a very small image initially and have that as a way to figure out if the scene is interesting. And then once you see that there's something interesting, you actually go back and capture the next frame, at higher resolution to get more, clarity as to what's going on. Or imagine you have other sensors like accelerometers that, are more low cost in terms of power, and then from those sensors you figure out when, there's a situation that likely nothing's happening. So maybe the person is just really still. Maybe you've got other things you're using, maybe physiological measures as well. and so you conclude that the chances are low that this is an exciting moment for this person, and so then you don't record. So I think we have to really kind of pursue those lines of attack and really sort things out. But I can imagine you might embed the sensing task here in a broader context, and in doing that, maybe there are strategies for being more conservative around power. So I think that this is an area that is really going to get a lot of attention as these devices become more prevalent. Certainly the smartphone manufacturers are worried about battery life, and they're doing lots of clever things to try to get their imagers as low power as possible. So that's a driver right there from the commercial side that's going to happen. And then we have these other strategies we can follow, because we're not trying to produce images for people to watch them, but only to analyze and get the information we need. So that's how I think we should approach it, and I hope within MD2K we'll actually start doing some of that work, as we go forward.
And what do you think about fusion with other lower cost or other sensors that may be embedded in the phone itself? So
yeah, no, I think that's also that's a great idea too, because again, whenever you've got a sensor which is really power hungry, what you tend to think about is just going to it a lot less frequently. So you might think about having a continuous kind of GPS plus accelerometry trace, and then maybe inertial sensor as well, and then a frame every few minutes or something. And so then you can think about how do you then combine those measures and get the valuable things from the image, but supplement with sensors that are less power hungry over the interval of time. So I think that's a very interesting thing to think about. I haven't really seen a whole lot of work along those lines. It would really depend on the task as to whether that was going to be viable. But definitely, if you think about like a kind of power accuracy trade-off, the more power you consume, the higher accuracy you can ask for. Then trying to push the vision sensor down into a place where it's giving you value in terms of accuracy, but you're then combining, but it's not the full power budget you could have, and then supplementing with lower power devices to make up the difference in accuracy. Those are very interesting trade-offs to explore, I think. The other thing I want to mention, just along these lines, that's I would say very far from commercialization, but there's quite a bit of work now on. I shouldn't say quite a bit of work. There are a couple of interesting projects now on essentially cameras that are powered like environmentally. So Josh Smith's lab at UW is working on cameras that are powered from Wi-Fi signals that are available in the environment. Sri Nair at Columbia University has a project on essentially a camera where you interleave what you can think of as solar cells with sensors. So you're actually using light energy to power the camera as you take pictures. I wouldn't want to create the impression that these are going to be on your iPhone next year or anything like that. But I do think this is an interesting space where there's lots of solutions to the power problem that range from very application-tailored solutions to just straight-up kind of technology innovations. And I'm hoping one of those horses will win the race and give us the capability to do this on a large scale.
Well, if there are no other questions, I guess we'll conclude. Thank you very much, Dr. Rehg, for a very interesting presentation. Thank you very much. This will be, the video of this webinar will be posted on our YouTube channel.